Hello friends, welcome back in this video session of heat source system of unit number 2 of subject heat transfer. My name is Mr. S.V. Kumbar, Assistant Professor, Sharad Institute of Technology, College of Engineering, Yadra, Ichalkaranji. Heat source system is also known as one-dimensional steady-state heat conduction with internal heat generation. So these are the contents of today's video lecture. We will see two derivation for plane slab with different boundary condition. One cylindrical system, that is electrical current flows through a conductor solid cylinder with different boundary condition. Before going to start actual derivation, we will see few examples. Now there are some practical applications of internal heat generation. First one, Joule heating in an electrical conductor due to the flow of current. Whenever current flows through a conductor, then there is a internal heat generation occurs inside the element, and that heat is dissipated to the atmosphere. Energy generation in a nuclear fuel rod due to absorption of neutron. So whenever there is an absorption of energy in a nuclear fuel, there is a internal heat generation within that rod. Third one, exothermic chemical reaction within a system. For example, combustion. In internal combustion engine, heat is liberated at a given rate throughout the system, and that heat is dissipated into the atmosphere by all three modes of heat transfer, that is conduction, convection and radiation. Few more example. In nuclear power plant, heat is liberated in shielding used in nuclear reactor due to absorption of electromagnetic radiation such as gamma rays. Whenever electromagnetic radiation, that is gamma rays, absorbed by shielding, then heat is absorbed and heat is generated, internally generated. Third, next one, curing of concrete. Whenever concrete is cured, there is a tremendous heat liberated throughout that concrete. Next, magnetization of iron. Whenever iron gets magnetized or demagnetized, then there is a generation of internal heat energy, and we can consider it as heat source system. Next example, ripening of fruits and in biological decay process. Generally, in ripening of fruits, tremendous heat is liberated into the atmosphere, and in second case, biological decay process where heat is internally generated and which is dissipated into the atmosphere. Now in a plane slab with uniform internal heat generation, we will consider two boundary condition. In first boundary condition, both the sides of the slab will be at the same temperature. This is our first consider. And second case is two sides of the slabs will be at different temperature. Before going to start actual derivation, we will state few assumptions. First assumption, one dimensional conduction only. That is, heat flows in only one direction, unidirectional heat flow. When the thickness L is very small as compared to y and z direction, then it can be considered as one dimensional heat conduction. Second assumption, steady state heat conduction. That is, temperature at any point within the slab does not change with respect to time, even though temperature at different points will be different. Third, there is a uniform internal heat generation in slab, that is at Qg rate watt per meter cube. Next, material of the slab is homogeneous, which is made up of same material, that is density remain constant, and the material which is used for the slab must be isotropic in nature. The thermal conductivity remains same in all the direction. Now we'll start with first derivation, that is plane slab with uniform internal heat generation, that is both the sides of the same temperature, right? So here the temperature at left hand side and right hand side will be same. Okay, let's say To is equal to 2 T max, that is at origin maximum temperature occur. K is the thermal conductivity of the material and Qg is the rate of internal heat generation. And observe here L is half thickness of slab. Now for above mentioned situation, governing equation in Cartesian coordinate can be reduced to d2t upon dx square plus qg upon k is equal to 0. This is the modification of general heat conduction equation in Cartesian coordinate, as heat flows along x direction only. So only first part is considered d2t upon dx square. The remaining two, that is d2t upon dy square plus d2t upon dz square, which will be equal to 0 because it's a unidirectional heat flow. There is internal generation of heat, and as it is a steady state, right hand side will be equal to 0. Now solution of this equation 5.1 gives temperature profile, and then by using Fourier's law we can get heat flux at any point. First we will define boundary condition. Now boundary conditions are at x is equal to 0, that is at x is equal to 0, that is origin. Here center line is origin, therefore x is equal to 0, t is equal to t max, and dt upon dx is equal to 0, right? And at x is equal to plus or minus L, t is equal to tw, that is the wall temperature of right hand side and left hand side. So integrate this equation 5.1 once, we will get dt upon dx. Take this qg upon k to right hand side, we will get on integration dt upon dx is equal to minus qg x upon k plus c1. Again integrate this equation so that we will get only t term. So integration of this would be t is equal to minus qg x square upon 2k plus c1 x plus c2. This is the integration of previous term. Now applying boundary condition, we will get c1 value as 0. Applying second boundary condition, we will get the c2 value as t2 plus, sorry, C2 is equal to TW plus QG L square upon 2K. Now substitute C1 and C2 back in equation 5.1. We will get Tx is equal to, that is temperature at any distance x, is equal to, first term will remain as it is, minus Qg x square upon 2K. As C1 is 0, this term will be 0. Directly we will write the value of C2 as TW plus Qg L square upon 2K. Now if you observe carefully, first and third term will have same quantities. So taking all those quantities in a common and write in a bracket, that is Tx is equal to Tw, this Tw as it is, Qg upon 2k is common, taking outside the bracket, L square minus x square, where L is half thickness of slab. Also by observation, T is equal to maximum temperature at x is equal to 0. Now putting x is equal to 0 in equation, earlier equation, we will get maximum temperature T max is equal to Tw plus Qg upon L square upon 2k. Now from equation 5.4 and 5.3, we can write T minus Tw upon T max minus Tw, which is equal to L square minus x square upon L square, which can be rewritten as 1 minus x upon L bracket square. Now if you observe carefully this equation, the temperature at any distance x from its origin is function of x square. It means that it follows a parabola. Therefore, the temperature distribution will be parabolic in nature, that we have already shown. Next part is convection boundary condition. In many practical applications, heat is carried away at the boundaries by a fluid at a temperature Tf flowing on the surface with a convective heat transfer coefficient H. For example, a current carrying conductor cooled by ambient air or nuclear fuel rod cooled by a liquid metal coolant. Then applying energy balance equation. It is the amount of heat conducted from within the body to the surface is equal to the amount of heat convected away by the fluid at the surface. So if A is surface area of slab normal to the direction of heat flow, we can write QGAL, which is equal to HA TW minus TF. Now from this we can write the value for TW. TW is equal to this minus TF is taken to right hand side. AA will get cancelled. H is divided here. So TW is equal to TF plus QGL upon H. Substituting this equation, we will get Tx, that is temperature at any distance x, is equal to Tf plus Qgl upon H plus Qg upon 2K into L square minus x square. This equation gives temperature distribution in a slab with heat generation in terms of fluid temperature Tf. Remember, L is half thickness of slab. Now heat transfer, we know that heat transfer rate either of surfaces must be equal to half of the total heat generated within the slab for the boundary condition of Tw being the same at both surfaces. That is Q is equal to Qg A into L. Here we complete first part of derivation. In the second part of derivation, the temperature of right hand side and left hand side of wall will be different. So second derivation is plain slab with uniform internal heat generation when two sides at are different temperatures. Let T1 is greater than T2 and Tmax must occur somewhere within the slab since heat is being generated in the slab and is flowing from inside to outside both the left and right faces. Let Tmax occur at a distance x max. Let Tmax occur at a distance x max from the origin as shown in figure. Here T1 is maximum, T2 is minimum, and somewhere between T1 and T2 there will be maximum temperature at x max distance of thickness of slab L. Let K is the thermal conductivity and Qg is the rate of internal heat generation. Now applying the same steps that we had applied for first derivation, T is equal to minus Qg x square upon 2K plus C1x plus C2. This equation we obtain by double integration of general heat conduction equation in one direction only, that is x direction. Here C1 and C2 are obtained by applying boundary condition. First boundary condition is x is equal to 0, t is equal to t1. Second boundary condition, x is equal to L, t is equal to t1. If you substitute these two boundary conditions here, we will get C2 as t1 and C1 as t2 minus t1 upon L plus QGL upon 2K. Substitute these two boundary conditions in this equation, we will get Tx, that is temperature at any distance x, is equal to minus Qgx square upon 2K plus T2 minus T1 upon L plus Qgl upon 2K into x plus T1. Multiply this x in this bracket and try to solve. Try to simplify as you can. We can get Tx is equal to T1 plus L minus x Qg upon 2K plus T2 minus T1 upon L into x. This equation is very important and it gives the temperature distribution in the slab of thickness L with internal heat generation and when two sides are maintained at different temperature T1 and T2. Right? Now we will locate the maximum value of temperature. Differentiate this equation with respect to x and equate it to 0, we will get the condition for x max, right? And if you substitute x max value in this equation, we will get the condition for maximum temperature T max. While solving numerical, I'll explain it once again. Heat transfer to the two sides, the total heat generated within the slab is equal to Q total is equal to Qg into A into L. Now remember, part of this heat moves to the left and gets dissipated to left face, and remaining portion of heat generated moves to the right side and gets dissipated from the right face. Applying Fourier's law of heat conduction, Q right is equal to minus Ka dt upon dx at x is equal to L, and Q left is equal to minus Ka dt upon dx at x is equal to 0. Now this equation will be negative since heat flows from right to left, that is in negative x direction. Therefore, total heat is equal to Q right plus Q left. Convection boundary condition. Let heat be carried away at the left face by a fluid at a temperature Ta flowing on the surface with a convective heat transfer coefficient Ha, and on the right face by a fluid at a temperature Tb flowing on the surface with a convective heat transfer coefficient Hb. Now, heat generated in the slab in the volume between x is equal to 0 and x is equal to x max has to move to left side, and heat generated in the volume between x is equal to x max and x is equal to L has to move to the right side, because no heat can cross at the plane of maximum temperature. So we can write on the left face Qg into A into x max is equal to HA into A into T1 minus TA. This is our A equation. On the right side, Qg into A into L minus x max, which is the right hand side of origin, which is equal to HB into A into T2 minus TB. From equation A and B, we can get the value for T1 and T2 in terms of known fluid temperature Ta and Tb respectively. And after this, we can calculate T1 and T2 in order to get the temperature distribution in terms of fluid temperature Ta and Tb. We will consider one example here for cylindrical element, a current carrying conductor. Consider a conductor of cross-sectional area AC. Let L is equal to length of conductor, I is equal to current flowing through conductor, rho is equal to electrical resistivity of the material. Then heat generated per unit volume, small qg, is equal to qg upon volume of conductor, where qg is the total heat generated, which is given as I square into R, and volume of conductor is written as area into its height. But R is equal to rho into L upon AC. Therefore, in this equation, we will replace the value of first Qg as I square upon R, and volume of conductor is AC upon L. After that, replacing the value of R by this equation, rho L upon AC, here we will get I upon AC bracket square into rho, which will be in watt per meter cube. Small I is known as current density, and it is given as capital I upon AC. Its unit is watt per meter square. So Qg is equal to I square rho, which is equal to I square upon Ke. Ke is known as electrical conductivity. Putting all these equation in this formula for temperature distribution in a current carrying wire or cylindrical or solid shape, that is Tr, temperature at any radius r, is equal to Tw plus Qg upon 4K capital R square minus small r square. Substituting the value of Qg, replace the value of Qg by this Qg, we will get Tr is equal to Tw I square into rho upon 4K capital R square minus 4 minus small r square. Maximum temperature occurs at the center of conductor. Therefore, putting R is equal to 0, we will get the condition for maximum temperature as Tmax is equal to Tw plus I square rho R square upon 4K. Now we will see one example. Heat is generated uniformly in a stainless steel plate having K is equal to 20 watt per meter Kelvin. The thickness of plate is 1 centimeter and heat generation rate is 500 megawatt per meter cube. If two sides are maintained at 100 and 200 degrees centigrade respectively. Calculate the temperature at the center of plate, the position and value of maximum temperature, heat transfer at left and right face, and sketch the temperature profile in the slab. So first of all, identify whether it is a first case or second case. That is, whether the temperature of wall are same or different. So if you read the problem carefully, if the two sides of the plate are maintained at 100 and 200, means it is our second case, right? So T1 is 200, T2 is 100. Okay, L, length of slab is given as 1 centimeter, that is 0.0 meter. Internal heat generation rate is given as 500 megawatt per meter cube, that is into 10 raised to 500 into 10 raised to 6 watt per meter cube. Thermal conductivity of material is given 20 watt per meter Kelvin, right? Considering second case, temperature distribution is given as Tx is equal to T1 plus L minus X Qg upon 2K plus T2 minus T1 upon L into X. We have to determine the temperature at center. At center, X is equal to zero point 0.5 centimeter. That is, X is equal to 0.005 meter. Substitute this value here, we will get temperature at center as 462.5 degrees centigrade. Now we know end temperature, that is at left hand side 200 temperature, at right hand side 100 degrees centigrade which is given, and at center the temperature is 462.5. Next we will determine the maximum temperature and its location. So take derivative of this with respect to x and equate it to 0. We will get x max as 4.6 into 10 raised to minus 3 meter. If you substitute x max value here, we will get maximum temperature as 464.5 degrees centigrade. Next one is to plot a graph. As T1, T2 value are given, we have calculated the temperature at center and the value of maximum temperature. So by knowing all the temperature, we can plot graph for this. So here we will conclude for heat source system. Thank you very much.